We continue to study constraint optimization, and we'll begin with one more example. Let's consider a problem. Given a function, we set a problem of maximization and minimization subject to constraint. We have learned that we need to start with checking NDCQ condition. In the form of verifying whether the constraint as a function, or rather its gradient, will turn 0 at some point. So our constraint is the function, and here we set it 0. Nabla, or gradient of G, is a vector. It can be 0 vector at the origin. But the constraint set defined by this equation doesn't have this point, so it doesn't belong. That means the origin, this point, the origin, to the set. And this is the set. We call it a constraint set. So we claim NDCQ holds. After that, we form Lagrangian function using the formula . And we set the first order conditions. And the final equation is the constraint equation itself. In order to solve this system of equations, we firstly, in the first and the second equations, move these terms to the right. After that, having in mind that lambda is not 0, it's clear that it's not 0, we divide left-hand sides by left-hand sides, right-hand sides by right-hand sides, and finally we get a smaller system consisting of two equations . And it's very easy to solve it. We get 2 points. The first point has coordinates . And the second point, let it be B, is a symmetric to a point with respect to the origin. So these are the critical points of the Lagrangian function. But we still are not sure whether these points are the points of maximum and minimum of the given function, 3x plus 4y. So we need to study carefully whether they are points of extremum. How to do that? So let's refer to the single variable calculus, and we know from this calculus that there is so-called Weierstrass theorem claiming that given a continuous function on a closed segment, such a function takes the greatest and the least values. So let me make the statement, precise statement, theorem. So the author is German mathematician of the 19th century.